Okay, so if you are gone today, it is February 13th, day before Valentine's Day, and we're going to start looking at now Newton's second law. So this is the relationship that I was hoping for you to discover is what I'm going to reveal here. And again, laboratory experiments don't always show the right relationships because of errors in our measurements and stuff, but this is what you should find. Mass and weight are related, but they are different things. Weight is a force exerted on an object by usually Earth, because that's where we're close by. The moon could also exert a gravitational force on objects, but the moon's gravity is different than Earth's gravity. So weight is a force exerted on an object by Earth. It's due to like a gravitational field. Close to the surface of the Earth, where the gravitational field is nearly constant, here on Earth, G is about 10. And it's pretty constant no matter where I go on Earth. We can relate weight to mass using this equation. It's a really simple relationship, and I was hoping for you guys to sort of discover that with that lab, is I take the mass of the value, the mass of the object, and I simply multiply it by g, the acceleration due to gravity. If g is about 10, then 1 kilogram of matter would weigh about 10 newtons. 2 kilograms of matter would weigh about 20 newtons. 5 kilograms would weigh about 50 newtons. All I'm doing is I'm multiplying the mass by g. If we use g as about 10, it's a really simple calculation. Mass depends only on how much stuff an object has. So mass depends only on how much stuff is in that object. It's a collection of atoms, if you will. And so mass is something doesn't change. When I take that object from here to the moon, its mass should be the same, but its weight would change. And that has to do with the fact that the moon's gravity is different than our gravity. By the way, this picture here, you guys ever see the movie Martian? The Martian? It's a pretty good movie. There's a lot of problems with the movie in terms of a science standpoint, but it's a pretty cool idea. Mars gravity, and it is a planet that we hope to actually go to at some point, is only about 3.7 newtons per kilogram, as opposed to here on Earth is about 9.8. So things on Mars would weigh less than they do here, about a little bit less than half. So if here on Earth, if you weigh 150 pounds, on Mars you would weigh more like probably 60 pounds. It just has to do with the gravitational field being weaker there. And so the newtons per kilogram is the unit that we would use for G. Now, it would be easier to lift an object on Mars than it would be here on Earth, but it would be just as difficult to throw. And the reason for that has to do with when you're throwing an object, you're sort of working against the mass of the object, mass, as opposed to the weight. When you're lifting something, it's more about the weight that you're having to work against. When you throw it, it's more like it presents some inertia. The inertia is related most to its mass. So when you're lifting an object, you're exerting a force against gravity. When you're throwing, the force that you're exerting is perpendicular to the weight, and so it doesn't really matter if it's weightless. It's got mass, and that's where the difficulty in throwing it would be. Now I'm going to take you guys on a little field trip to the moon, but it's a fake field trip. So in the back, I'm going to ask you guys to come over here and try this. So I have six different weights in these things over here. So just come on back for a minute. And so on this side, I have a 1 Newton object here on Earth, and on this side over here, I have what it would feel like on the moon. So I have 6 setups, so we have 20 in here, so not everyone can do it at the same time. But what I'd like you to do is I'd like you to pick up one of those and pick up one of those. You just hold those in your hand. So again, I only have 6 setups. I don't have enough of one. So just come around, grab those. I want everyone to feel this. So yep, come on over, one of those and one of those. One in one hand, one in the other. Taking you on a field trip. So again, I only have room for 6 for right now. But so you just have to hold off for a minute. I'm going to give you something to do with these things. So one of these, one of those. There's still 2 more here that we can do. All right, now, for you guys, I want you to get a sense of this. Yep. And then everyone will get a chance at one point. I put these in cups because your sense of weight is oftentimes disrupted by a density idea. So in your hand, you should feel the same kind of object as a cup. Here on Earth, this thing weighs about 1 Newton. If you were to go to the moon, that's how heavy it would feel. So this is what it weighs here on Earth. If you took that object to the moon, that's how heavy it its weight is about 1/6 as strong as it is here. So in one hand is what it would feel like on Earth. On the other hand, it's what that would feel like on the moon. Yeah, that's fun. You can sort of sense that. It's certainly easier to lift the one that's in that lighter cup, right? That's what it would feel like. On the moon, that object that's in your right hand would feel as heavy as it is in your left hand. Now, when you shake the one in your right hand, shake the 500 grams. That's exactly what that would feel like if you shook that one on the moon. Because when you shake it, it's the mass of the object that you're working against. This here would feel like that if you shook it on the moon. We don't get a chance to go to the moon often, but that's what it would feel like. I want each person to have one of these. So try this so you can get a sense of that. It's important for you to feel that sensation. So in one object, you have a 500-gram cup. In the other object, you have about 80 grams. So yeah, try it. I want you to feel it. So if you haven't done it yet, it's an important understanding there. So just take a minute, try that out. We'll set. That's for my wave stuff that we're doing. So yeah, I want each person to get a sense of that, right? So yeah, one thing here on Earth, it would weigh something different on the moon. When you're done, and you feel like you've had a chance to be able to do that, put those back on that back table and then head on back to our seats. If you missed this thing here as a activity, people were feeling what things would feel like on a different planet in terms of their weight versus their mass. All right. Field trip to the moon. It's always fun. Guys, we're going to formalize now Newton's second law. Probably the most fundamental of all of the laws of physics is this law. We use it for a lot of things. Newton's second law just shows us how force, mass, and acceleration are related. It's a very simple law. We would say F equals m times a. So the left-hand side represents the total amount of force. Now, it could be 3 or 4 things that are exerting forces on an object, so we'd have to consider which way they're pointed and stuff like that. The left-hand side, total amount of force. The right-hand side involves mass, and then the other thing is acceleration. Now, I'm going to rearrange this equation for acceleration. I'd say A would then be equal to the net force divided by the mass. We would say acceleration is directly proportional to force and inversely proportional to mass. Now, that idea has to do with where the F and the M are in that equation. When I say two things are directly proportional, that means doubling the amount of force acting on an object would double the acceleration. Those are in direct proportion. One goes up, the other goes up by the same quantity, by the same factor. In inverse proportion shows that if I double the mass, I would have the acceleration. So that equation is a very simple equation. A is F over m, and that's how we would say how force sort of causes an object to change its motion. We could say force causes an object to accelerate, whereas mass sort of resists it. Very simple relationship. Yeah, it's the foundation for all changes in motion. All changes in motion when I call macroscopic, what I'm talking about is large scale. That's bigger than atoms. So anything at all. And so, Bree, I'm going to pick on you for a second. You're softball pitcher, right? So in order for you to take them all, would you mind sharing really quick what your top end speed? What are you able to get that ball to travel?
67.
67. Now that sounds pretty good. That's pretty good speed, right?
Yeah.
So what Bree is able to do, and again, I can't do the wind up, all that kind of stuff. That I was a high school pitcher, but high school pitchers, they have a much different kind of wind up than softball. But anyway, Bree is able to take that ball from rest. It starts at rest, and during the action that you're going through, you're taking that ball from 0 to 67 miles per hour. That requires, we would use Newton's second law to look at that to say, the force that you're exerting, highly variable throughout, but by the time you're done, the force that you exerted took that ball from 0 to 67 miles per hour, and we could use that law to sort of describe how that force, mass, and acceleration relate. Step on the gas of your car. Your car is 1,500 kilograms, much more massive than a softball, but you step on the gas of your car, the engine turns the wheels push on the ground pushes the car forward. The force needed to accelerate your car described by that equation. Everything, macroscopic. Now, if I'm dealing with atoms, I can't use Newtonian mechanics. I'd have to use quantum mechanics. And so that's, quantum is for the microscopic. So for this one, it's for any kind of thing that we would want to know. F equals m times a is fundamental. Okay. Now, this is about proportional reasoning. You won't need a calculator for any of this. If this is my base case, a base case is the thing that I would look at to determine what happens. So the force of the hand accelerates the brake, pushes it to the right, produces a certain amount of change in motion. If I push with twice as much force, so instead of just one hand, if I push twice as hard, that should cause the brake to accelerate twice as much. So we would get 2 times as much acceleration there. If this is the base case, if that's the base, force of the hand accelerates the brake. If I exert the exact same amount of force on 2 brakes, what should that cause? That would be half as much acceleration. So again, one is showing that if I apply twice the force, I should get twice the acceleration. But if I apply the same force on twice the mass, I get half as much. Now, let's try this one. If I push 3 bricks with the same amount of force as I push 1, how much acceleration should I get? Don't need a calculator for this. Should get 1/3 as much. The trickiest one is the one that I've left up there yet for us to look at. What if I push with twice the force on twice the mass? What kind of acceleration should I get? If I go down this way, if I push twice as hard on twice as much mass, what kind of acceleration should come out? Tell that person that you're sitting next to. What goes in there? Anyone willing to take a risk? Try it? Thanks, Bradley. Should be the same. The idea behind this, and this is why, and I want to take a moment and make sure you understand why it is that these 2 things that are greatly different weights, I think Izzy can verify. Izzy can verify. Which one's heavier? By how much would you say? It's about 3 times heavier. Okay? Tennis ball, baseball, 3 times heavier. But when I let them go, they both accelerate equally. And the reason for that is I've got 3 times as much force acting on 3 times as much mass. So if the amount of mass increases proportionally to the amount of force acting on it, I see that they would accelerate at the exact same rate. If I take a car that's 1,500 kilograms, and this is 1 kilogram, the car is 1,500 times as massive as this, which means it's 1,500 times as heavy. I let them go, they should accelerate equally. So it's an explanation for why objects accelerate at the same rate, not just that they do, right? 3 times as much weight on 3 times as much mass is the same acceleration. Okay. I didn't need a calculator for that. We will need one for these. So when we go to solve problems using Newton's laws, sometimes we have to be able to use a calculator to go through and do this. I'm going to ask you to draw a force diagram for this. So we have a bobsled being pushed by 2 athletes. We have Bob and Tom. Bob pushes with 250 newtons to the right, Tom with 220 to the right, and the ice is also able to exert forces. The ice exerts a force on the tracks that's 50 newtons to the left. I'd like to know what is the rate at which that bobsled changes its motion. So the rocket sled activity was to help you be able to draw a force diagram. I'm going to let that dot represent the bobsled. Now I'm using color coding, so it's easier for you to see that these forces are due to various objects pushing on this. That's the bobsled. Now, the Earth pulls down on this thing with a certain amount of weight. That's how heavy it is. If we say G is 10 newtons per kilogram, and this is a 75 kilogram bobsled, how heavy is it? 750 newtons. So I would put on this thing, that is a 750 Newton weight force. And I know that because here on Earth, the Earth pulls on that object with a force of 10 newtons for every kilogram. Okay. Do you guys agree that ground has to exert an upward force to keep it in a state of equilibrium? That upward force, I'm going to do that as a sort of like a ground force up. Would you guys agree that it'd have to be 750 newtons? That comes from the ice sort of buckling a little bit underneath the weight of that bobsled. When I put the masses on the meter sticks the other day and you saw the meter sticks buckle a little bit, that upward force balances the weight, keeps it in a state of equilibrium vertically. Now you have Bob and Tom that are pushing, so I'm going to go ahead and use two different forces here. So that's the force from Bob. And Tom pushes a little bit less aggressively. And then I have one more force that's acting. And that's because the ice is able to exert a little bit of a frictional force to oppose that motion. That's 50 newtons sort of opposing it, so there'll be 50 newtons to the left. Let's go ahead and draw that this way. So oftentimes what we have to do when we're solving Newton's laws problems is we have to visualize the forces that are acting. Which way do they point? How big are they? What are they due to? Stuff like that. So I'm using color coding to denote 5 different objects that are exerting forces. One's the earth, one's the ice, one's Bob, one's Tom, and the other is the ice or friction. So all 5 of those forces are indicated. If I want to determine the acceleration, I have to determine the net force and then divide that by the mass. Are you able to look at that diagram and determine what the unbalanced force is? Got 5 things there. But when you add them up, including their direction, what's the total unbalanced force? And how much? In which way? Can you do it? I see vertically they add to 0. But horizontally there's an unbalanced force towards the right. What is that value? 250 plus 220 minus 550, is it 420 newtons? Okay, so the numerator is 420 newtons. That's unbalanced towards the right. The denominator is the mass of that bobsled. That bobsled, I know it says its weight is 750 newtons, but what goes into that equation is its mass, not its weight. And so when I go to calculate things like Newton's laws, or in this case the acceleration of that, I have to consider which way those forces act and how much mass acts that it's acting on. When I do that, I get 5.6. Now, technically I could write newtons per kilogram, but the better unit for that is to say that is equivalent to something called meters per second per second. So even though that's what the equation gives me, that really is the same as 5.6 meters per second squared. And so that would be the rate at which that bobsled is changing its motion using Newton's second law. Importance of being able to visualize which way those forces act. Understanding the difference between mass and weight. And that would be an example problem for you. Okay. I don't know about the other one here. I want to see if you guys can visualize what would have to happen here. So what net force is needed to accelerate a 1,200 kilogram car from rest to a speed of 3 meters per second in a time of 5 seconds? So I'm asking for this one, how much net force is needed? I'm going to go right to Newton's second law. I just want to know the total unbalanced force. So I'm not going to care about what kinds of things act in which direction. I just want to know the net force. That's the left-hand side. I know it's 1,200 kilograms. But how can I look at this and determine what the acceleration for this car is if I know it needs to get to a speed of 3 meters per second in 5 seconds? We recall that A is equal to the change in velocity divided by the time that it takes. So if I'm going to go from 0 to 3 meters per second in 5 seconds, that's how I calculate the amount of net force that's needed. Three divided by 5 is 0.6. So we would say that that is 1,200 kilograms. And I see that I would need 720 newtons of net force to produce that kind of change in motion. Okay? Questions for me? This is the quantitative law. This is the one that shows how force is related to A, the acceleration of an object. Occasionally we have to draw diagrams to determine what that net force is. Other times we have to use other equations to be able to do that. This is the hard part of this unit, is dealing with that equation. Okay? Okay, I'm going to stop the video there. If you're in the event that you're having to watch this from home, hopefully that helps you a little bit.